Hello everyone, my name is Roshan Kharka and we team 13 are here to present our project report and
Sorry. Yeah. Okay.
yeah, and the title of our project is Inverted Pendulum on Cart. Uh, Inverted pendulum on a card system, and we are using the two controller method for to design the block diagram on the Simulink, and the two controller methods are LQR and pole placement method. LQR represents the linear quadratic regulators. So the problem statement here in our project is we have to design the Simulink model of the inverted pendulum on a cart using the provided linear state space plant, and we have to use the two different controller methods, and we have to use the same plant for these two controller methods, and we have to provide the one dashboard interface that sets the initial angle, and here the initial angle we have to set is from -15 to plus 15 degree. So here we had built the Simulink model of the inverted pendulum, and here we had designed two different state feedback controller, that is LQR and pole placement, which I had told already, and we had connected the same plant for these two controller and get the result, and we at last we compare the controller result performance at the plus minus 15 degree initial angle. So, and also we had also provided the interactive dashboard interface in the Simulink model, and also the actuator saturation where we put the value from plus 20 to minus 20 Newton. And so to do this, we had given this Langarian equation, which is non-linear equation, this equation, and this equation is mainly useful to calculate for the higher angles. So we have to convert this Langarian non-linear equation to linear state space equation. So here are the values of this. Uh, mm, mm, here are the given values, and the thing this NCMP represented is the here the MP represents the point mass, and the MC represents the mass of the card, and the length represents the length of the rod. And here we had assumed the rod weight is weightless, and the Q1 is the card displacement, and the Q2 is the pendulum. The Q2 is the pendulum angle for our card, and the U is the horizontal 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 force applied to the cards, and D1 and D2 represents the damping present in our card. So we had converted this into linear state space equation, and the equation is seems like this, and the value of A and B in the matrix forms are this. And as we had already given this value of these parameters, so we put these values, and we had write the MATLAB code for this, and the code for the MATLAB here mm, is which one is the here, and so the code. So here is the code for our project, and these are the given parameters, and we are converted our non-linear equation into the linear, and we get these values for the A and B, and the value for the A is 4 into 4 matrix, and for the B is 4 into 1 matrix, and we are using the initial angle 5 degree here, but we will change this later while we will construct the Simulink model. And the code for the our controller A is this, and controller B is this. So now I'll show you the Simulink model, and my friend Santos will describe the blocks for this model.
Let me continue with from here. So, hello everyone. My name is Santosh Subedi, and Helen, you can see me. So our part is divided into the three parts. So all the introduction that has already done by the Rosans, and all the simulation block I will continue from here. So all the parameters that has given by the professor and the problems that has given by the professor. So I will explain into the simulating block, and then after my friend, our team member, three member, Halloween will continue all the output data in the last. So let me begin with from the a Simulink block here. So I'll take you to the or directly to the Simulink block. So let me share my screen. So here is the Simulink block we have here. So can you see the Simulink block, Helen? Okay, so you can see, right?
Yeah.
I'm just confirming it either he's seeing or not. Oh, is you yeah, that's oh you this screen is sharing. Okay. So let me start with problem that we have given here. So I'll just go to the another screen that is the problem that is given by our professor. So to get into the Simulink, so for first we need to see the all the problem that has given by our professor. So the problem statement is to build a Simulink model of inverted pendulum on cart using the provided linear state. So as my friend already said that how we converted all the non-linear into the linear state space, so that has already done. So initial condition that we have given value here is 5. So we'll convert that 5 into the plus minus 15 degree, that is in the degree will later in the Simulink. So here, so the initial condition here in the block is the to add the knob for the initial angle. So here you can see that the initial angle we have given here, so we have created the knob here. So that is the knob for the angle. So here we can change the all the value from like whatever you want, but our given is minus 15 and 15. So that 5 will convert into this value, so minus 15 and 15. So we can change the all the value as well. So if you want to see the output in the 20 degree and minus 20 degree, that shouldn't be a problem, but the system will respond differently. So the standard value here we have put here is minus 15 and 15. So that's how we have created the knob here. So this is the knob, and another the key thing we have to set is here is the initial value. So initial value is the cart should be in the zero condition, like it's not moving. So that's why all the condition here is a 0 0 0. So further, to get the good output, so we need to use the controller. So controller, here we have a many option for the controller. So here we have choose the two controller method, that is one is the pole placement and another LQR. So this both gives the good result, that's why we have chosen. So that's why we didn't go for the PID lead and others. So we have to show this in the same dashboard. So that's why we have created the dashboard here in the same created. So I'll explain from here. So here you can see that we can change the all the LQR and post pole placement from here. So if you want to see the result output here in our graph, so you can change the LQR value like a pole placement, either from the pole placement or from the LQR. So we can change the toggle here. So if you want to see like minus 50 degree in the LQR, you can get the result from here. So you can see the change graph here. So this is the value we get. So if you want to see the close placement, so you can get the value from here. So that's the output result we will get from here in dashboard. So let me explain with this all these things. So as the problem stated that we have to feed all the pole placement, all the both controller into the same plant in the same dashboard. That's why we have put all those value in the same plant. So we have uh, created the closed loop system as well, so using the MATLAB function. So that's why we have created the closed loop function. To reason why we are creating the closed loop system is to stabilize the system. If you don't choose the closed loop systems, then the that may fail. So that's why we have chosen this. So here, so the switch block also here is created to to filter the value. Either we are choosing the LQR or pole placement. So this will give you the one value, and this will go into the this in MATLAB functions. And we have created the actuator here. So actuator, we have given the value of -20 and 20. So the maximum value that control force will give you till 20 and -20. So that's the actuator. So here, so the actuator, the value will go into the directly into the plant, and all the value that are coming from here, so that will go to the plant. So after that, we have output from the plant. So we have this splitted the value using the mux. So demux, so the Q1 and Q2 is now coming outward from the here. So this will give you the another scope dash Q1. So here we have changes the value into the absolute value, that will give you the positive value here, and it will store into the this memory. This store memory will go into the this dashboard we have display here. So all the graph will show here, and all the peak u, the value, the store value will go here, and the Q1 value which is stored here will go to the this here, and the Q2 value will go, I'll show you the Q2 where it is. So that's the Q1, and these all are these, and these are the optional block that I have created here. So for if you want to see the animation and something like that, just we can go to I have created the all the what do you call coding here, so to create the on the simulation, that's the animation, so the which is optional. So main thing, we have to get the all the Q1, Q2 and UN value here. So the reason that we are showing all these thing in dashboard is because our professor in our problem so already asked that all the ports, all the controller, all the outputs should be in the same dashboard. That's why we have created the same dashboard to get all the value. So from here, all the values are in the absolute value. So my conclusion will be, if you from our value comparison, the comparison for the LQR controller and the pole placement controller based on the simulation result at the initial pendulum angle, and on the plus 15 degree and minus 15 degree. The considering the maximum pendulum angle, both controllers show the nearly identical peak values, but here I can say that the LQR is doing good because it has a low control force as compared to PP model. PP pole placement has a more control force, which require the more saturation. More saturation means more actuator. That actuator could have the higher mass, so that is very difficult to implement in the real life. So we can give the real life example as well from here. So if you need if you are creating any project that require the response time is very quick, that we can go for the pole placement. If you need a like a controller force, like in lower controller, like in lower force, we can go for the LQR model. From now onwards, my friend will continue. Hello.
Okay, can you hear me?
Yeah, I can hear you perfectly. So I'll stop the sharing and you can start the sharing. Okay.
Yeah, let me share my.
Okay. Yeah, we are seeing.
No, Howlin,
You
you are on
you
mute.
are muted, sir. Just unmute yourself.
You are on mute mode.
You can unmute yourself. Oh yeah, I okay.
Yeah.
Yeah.
Yeah. Can you look the pre?
Yeah, I can see that. You can just continue.
Yeah. Here is the data generated from our model.
Mm-hmm.
Now let me show you the overall comparison of our two controllers. This table shows the results when the initial angle is set to plus 15 degrees. Let us go through each row. The first row is the peak angle. Both controllers showed 15.19 degrees. This is slightly higher than the intro 15 degrees. The reason is that at the very beginning, the pendulum keeps failing for a short time before the controller reacts, so the peak goes just a little bit above 15. Both controllers have the same value here, so there is a tie. Next is the chat displacement. Poor placement moves the chat only 0.547 meters. LQR moves the chat 0.741 meters. That means poor placement reduced the chat travel by 26%. Why? Because poor placement reacts faster, so the chat has less time to reflect before the pendulum is stabilized. Now look at the control fault. This is the peak force sent to the chat. LQR only needs 21.18 newtons. Poor placement needs 38.43 newtons. That's almost double. LQR used 45% less force. The reason is that the LQR mentioned directly tries to minimize control of force through its cost function. Poor placement doesn't consider injury at all. It just places the pole where we want them. For setting time, pole place sets in 3.19 seconds, while LQR takes 6.66 seconds. So pole place is 52% faster. This makes sense because the slowest pole placement pole is at -2, but the slowest LQR pole is only at -0.92. A bigger number means faster decay. The last row is overshot. This means how much the angle goes past zero in the opposite direction. LQR has 33% overshot, and pole placement has 47%, so LQR gives a smoother recovery. To summarize the table, pole placement is faster and moves the chat less, but LQR use much less force and has less overshot. Here is the clear trade-off. Now an important question, how do we know our simulation is correct? We verify the results using simple math. At time 0, the pendulum is at 15 degrees, which is 0.2618 radians. All other states are 0. So the intro control force is simple K2. The second element of the gene vector times the intro angle. For LQR, K2 is 79.89. Multiply by 0.2618, and we get 20.91 newtons. Our simulation measured 21.18 newtons. The difference is very small, only about 1%. This small difference comes from the simulation running for a teeny time step before mentioned the peak. For pole placement, K2 is 144.94. Multiply by 0.2618, and we get 37.95 newtons. The simulation mentioned 38.43, again very close. We also checked the setting time, the radio of LQR setting time to PP. Setting time is 6.66 over 3.19, which equals about 2.1. The pole location ratio is 2.0 over 0.92, which equals about 2.2. Their two reaches are very close, which confirms our simulation is correct. Let me now simulate the 5 most important findings from our project. Number 1, setting time. pole placement is 52% faster. This is a decreased result of this pole being farther left in the complex plan. The dominant pole at -2 gives faster decay at than LQR's dominant pole at -0.92. Number two, chat displacement. Pole placement moves the chat 26% less, even though LQR has the weight on chat position in its cost function. The slower response gives the chat more time to draft, so fast control actually leads to less chat movement. Number three, control effect. LQR need 45% less peak force. This is the main advantage of LQR. The cost function includes a team that penalize a large force, so the optimizer naturally found a solution that use less energy. Number four, on gray recover. Pole placement had 47% overshot, while LQR has only 33%. The large pole placement gains cause the Andre to shot plus 0 before coming back. Number five, and this is very important, is the saturation effect. Our actual limit is plus or minus 20 newtons. Pole placement needs 38 newtons, which is almost double the limit. So the force gets cut in half at the beginning. This means pole placement lost its advantage when saturation is activated. LQR only needs 21 newtons, which is just barely over the limit. So LQR performance is almost unchanged. So which control should be choose? The answer depends on the application. If the actuator is powerful and there is no saturation limit, the pole placement is better choice. It gives faster setting, less chart movement, and overall better dynamic performance. However, in our system, we have a 20 Newton saturation limit. This limit is very tight. Pole placement peak force is 38 Newton, which is 22% over the limit. The force single gets heavily clipped. This means the control can't do what it wants to do, and the performance drops significantly. Therefore, for our system, with the 20 Newton limit, we recommend LQR as a more practical and robust choice. Let me now wrap up our project. We started by model the invite probe on the chat using long-region mechanicals. We drawing the non-linear equations and then linearize them to get a state space model with 4 states. We then design 2 controls. The first one is LQR, which minimize cost function that blends Android recovered and control effect. The second one is pole placement, which discretely assess the closed loop pole to distract locations. We also build interactive Simulink dashboard for testing and both controls stabilize the system at 15. For the work, we could explore non control measures like sliding model control to handle large angle, or swing up control to bring the bloom from the hanging position to the upright position. So thank you very much for listening. We are happy to answer your questions.
So thank you, Helen. So from here, I will stop. Can you stop to share this your slide. So then I will show something. So I'll wrap up then.
Sorry.
Okay, so thank you so much, Helen. So as already Helen compared all the results that we got from our project. So I'll just go through the simulation block that how we got all this value. So here, so we can say all the value, like all the value from here. So we can see that like LQR we can choose from the PP plus placement. So we can choose all the value like -15 or 15 from here. So as you share the time angle, so we can run the program. So all the stop time is 10. So we don't need this one. So the graph is here, all the values that we were talking about, all the compare. So we got all the value here. So the as we doing all the inputs like LQ, pole placement, and both will give all the different value here, all the different value here in the QI, and Q2 and Q1, and all the graph will be slow. All this oscillation is showing based on this PQ, Q1, and Q2. So from this from this Simulink block, what we can say that is we can okay, let me just close this one and then I'll wrap up what I can say that is that the LQR is a preferred because it achieves the stabilization with significantly lower control effort and smoother response, making it more practical and robust despite a slower resetting time. Like if you are in the industry of the robotics or something like that, we can go for the pole placement. So for the industry like car manufacturing and all the industry, so we can go for the LQR because LQR gives you the best result in the lower control effort. So that's our project, and this is all about our project. And we have made all the criteria that has given by our professor. So as we can see here, so robustness, control effort, big, and everything. So thank you so much. Thank you so much, my team. So thank you so much. I think we are out of the time right now, so I'm closing it. Helen, are you there?
Yeah. Yeah.
So we are I am stopping this one. So I will share you all the recordings. Then you can upload in the practice space as well. Okay. So I think we all have to upload the video and a report as well. So I will share you the another PPT that is based on the templates, same templates, but I have made that template according to our university standards. So you can upload that one. Okay.
Okay.
Do you have any questions too?
No.
Okay, best of luck. We'll give the best in like presentation in the class. Okay.
Yeah.
Okay. Okay.
Okay.
Bye.
Bye, Helen.
Okay.
Bye. Have a
Goodbye.
good. Bye.